Here are two more examples of evaluating trig with inverse trig. We're going to use this flowchart that we've been using. So if you want to copy this flowchart to follow along with, check the video description. There's a link in there. You can click that link, open this up, print it out, and follow along if you'd like. Okay. So example 13, inverse tangent of cosecant of pi over 12. So starting on the flowchart here, is there a domain violation? No, there's not, because cosecant of pi over 12, that's totally fine. Pi over 12 is inside of the domain of cosecant. That's totally okay. We can do that. That's fine. And also inverse tangent, the domain is all real numbers. So you can take any real number at all and just shove it inside the inverse tangent function and you're good to go. Okay, so no domain restrictions here. Okay, so that's all fine. So is there a domain violation? No. Is the function paired with its own inverse? No, it's cosecant with inverse tangent. So it's not tangent and inverse tangent, it's not cosecant inverse cosecant, it's cosecant with inverse tangent. So is the function paired with its own inverse? No. Can the problem be solved using the unit circle? In other words, is pi over 12 a nice angle on the unit circle? No, it's not. It's not pi over 6, pi over 4, pi over 3, pi over 2, etc. It's not something nice on the unit circle. So no, we cannot use the unit circle to solve the problem. Can the problem be solved using the unit circle? No. Is the inverse function on the inside? No. Inverse tangent appears on the outside. The regular function is on the inside. So no, the inverse function is not on the inside. Is the inverse function on the inside? No. Follow the no path up here. Is the function paired with its own inverse? And again, we've seen this in the last few examples now. Even though we did already ask this before, we have to ask it again because it does affect what happens next at this point. So is the function paired with its own inverse? No. It's cosecant with inverse tangent. Is the function paired with its own inverse? No. Is the function paired with the inverse of its cofunction? So we saw that in the last couple examples too, and remember that sounds like a mouthful, but it's really not that bad. Is the function paired with the inverse of its cofunction? So let's write down what that is. So here's the function, here's the inverse function. Is the function, is cosecant paired with the inverse of its cofunction? Okay. Okay. Is cosecant paired with the inverse of its cofunction? What is its cofunction? Is cosecant paired with the inverse of its cofunction? Well, since it's cosecant, the cofunction is secant. What is the inverse of, oops. What's the inverse of that? The inverse of secant is inverse secant. Okay. So is cosecant paired with inverse secant? No, cosecant is paired with inverse tangent. So the answer to the question then is no. Is cosecant paired with the inverse of its cofunction? No, because the inverse of its cofunction is the inverse of secant, which is inverse secant. And cosecant is not paired with that, it's paired with inverse tangent. So is the function paired with the inverse of its cofunction? No. So we use a calculator. So. Okay, now I do want to point out that in some specific cases there may be some crazy trig identity somewhere out there that you could use to manipulate this and that, but it might cause a big mess. And for this specific example, there's nothing we could do like that. So let's go ahead and just use a calculator, like the flowchart says. So we'll zoom in here. So we want the inverse tangent of cosecant of pi over 12. So let's just do it all at once rather than pieces at a time. So inverse tangent of cosecant. Remember, cosecant is 1 over the sine, right? So we're going to say 1 over the sine, 1 over the sine of pi over 12. Okay. So inverse tangent of cosecant of pi over 12. So that's inverse tangent of 1 over the sine of pi over 12. And then that's going to give us approximately 1.3175 if we want to round to 4 decimals. So if we zoom back out a little bit, this is approximately 1.3175. Okay? And again, make sure that we were in radian mode when we did this in the calculator. Make sure that we're in radians. So that's example 13. Now example 14, let's go ahead and do this. Okay, so let's erase some of this stuff here. Okay, so example 14, inverse sine of cotangent of 7.2. Let's go back to the flowchart. Is there a domain violation? Well, let's see. cotangent of 7.2, is that okay? Yeah, we can take the cotangent of 7.2. That's not a domain violation. That's totally fine. How about the inverse sine of cotangent of 7.2? That's actually, we're not really sure about that. So we're going to have to go back to the calculator and double check. So remember, if we take the inverse sine of something, it has to be between -1 and 1. What I mean is, when you take the inverse sine of something, the something inside of here has to be between -1 and 1. So remember, the domain of the inverse sine is -1 to 1. So if you take the inverse sine of something, that thing better be between -1 and 1, or else you can't do it. So we have to make sure that cotangent of 7.2 is between -1 and 1. And is it? So let's, so we'll just keep it down here and zoom in. So remember, cotangent is 1 over tangent, so 1 divided by the tangent of 7.2 is about 0.7665. So since cotangent of 7.2, we just found out that cotangent of 7.2 is between -1 and 1, so it's okay to take the inverse sine of it. Okay, it's okay to do that. So is there a domain violation? No. Okay. Is the function paired with its own inverse? No, it's cotangent with inverse sine. Cotangent inverse sine. So is the function paired with its own inverse? No. Can the problem be solved using the unit circle? In other words, is 7.2 a nice angle on the unit circle? Absolutely not. It is not at all. So no, we cannot use the unit circle to solve this problem. Can the problem be solved using the unit circle? No. Is the inverse function on the inside? No, inverse sine appears on the outside, not on the inside. Inside is just plain old cotangent. The outside is inverse sine. Is the inverse function on the inside? No, follow the no path up here. Is the function paired with its own inverse? And again, we asked that before, but we have to ask it again here because it does affect what happens next. Is the function paired with its own inverse? No. Again, it's cotangent with inverse sine. Is the function paired with the inverse of its cofunction? So just like in example 13, we're going to go through that again. So we'll zoom back out a little bit. What's the function? The function is cotangent, so then what we want to do is ask ourselves, is cotangent paired with the inverse of its cofunction? Okay. So in other words, is the function paired with the inverse of its cofunction? Is cotangent paired with the inverse of its cofunction? What is the cofunction for cotangent? Cofunction is tangent. What is the inverse of tangent? It's tangent inverse. Is cotangent paired with tangent inverse? No, cotangent is paired with inverse sine. Okay, so cotangent is not paired with inverse tangent. Cotangent is paired with inverse sine. Okay, so the answer to the question then, is the function paired with the inverse of its cofunction? No, so we use a calculator. Which is nice, that simplifies it a little bit. Okay, so zoom in back to the calculator here. Now I want to point out that, remember earlier, way back in step 1 when we looked for the domain violation, we found this 0.7665-ish. I want to point out that it's probably a bad idea to do this, 0.7665, because if you round too much too soon, your final answer might be off by a little bit. So what we want to do is just do it all at once. So inverse sine of 1 over the tangent of 7.2. Okay, because what we want, remember what we wanted was inverse sine of the cotangent of 7.2. That's what we want to evaluate. Okay, and what we're doing is using a calculator, so we're going to have inverse sine of the cotangent of 7.2. Okay, then when we evaluate that, we get about 0.8734 if we want to round to 4 decimal places, 0.8734. Okay, so let's zoom out a bit. And that's our final answer, approximately 0.8734. Okay, so that's it for example 14. So that's 2 more examples of evaluating trig with inverse trig functions. And that's another example of using the flowchart here. So now we've gone through all the possible paths in the flowchart over the past 14 examples.